Alright, so exponential decay is very similar to exponential growth. It follows a very similar pattern. The only difference is that the growth rate is negative. Okay, so when the rate of growth of a function is proportional to its value and the growth rate is negative, the function exhibits exponential decay, i.e. the higher the value, the more quickly the function decreases. So here we've got the value of the function. Let's just call this f of x. Let's call this x. Okay, so here, the value of the function is quite high, right? Well, it the function is also very steep, but the slope is negative, right? So it's decreasing very quickly. Here, the value of the function, is lower, and it's also less steep. It's kind of the slope is kind of evening out, and even more so down here, right? So the value of the function is lower, and the slope is getting better, and then actually the slope is approaching horizontal over here. So the growth rate um, is negative. The slope is negative here, but it's getting gentler and gentler as the value of the function decreases. Right. So that's the pattern of exponential decay. Um, and so an example would be radioactive decay. If you've got like a bunch of mass of, let's say, uranium, when it's got a ton of mass up there, it it that uranium decays. I think it. Let's see. What becomes lead? Maybe it's plutonium that becomes lead. Anyway, it decays to the next to the byproduct element, right? So there's a bunch of mass there, and it's decaying very quickly. Well, now it decays to this point, and it's decaying more slowly. And then when there's just barely any of the original amount left, it's decaying very, very slowly. Yes. So here's the basic structure of the equation for something that exhibits exponential decay. And there's other ways of writing this. I mean, you call it, maybe sometimes it's like y equals a 1 plus negative r um, to t, something like that. I'm going to write it this way. So this says the value of the function at time t. Maybe if you're measuring time in years, we say like x of 3 is blah blah blah. Equals the value of the function at time 0, meaning what you start with, times 1 plus the negative growth rate. So if the growth rate is negative 4%, it'd be 1 plus negative 0.04. In other words, 0.96. Raised to the power of t. The in the case of 3 years, you'd say raised to the power of 3. So that's basically how it works. And let me see. Is there anything else to say? That's the basic idea. Um, the value of the function at a certain time. So the growth rate will be in terms of a period of time. So, for example, negative 4% per year, or negative 4% per day, or negative 4% per second. So then the time elapsed would be in terms of the period of decay. So if there's something that exhibits a growth rate of negative 4% per year, then t would represent years. Or if you're talking about half-life, then t would represent the number of half-lives. If the half-life of something is 6 billion years, then x of t would be 2 cycles of that half-life. And so if the half-life is 6 billion years, then that 2 would represent actually a period of 12 billion years. 2 of those half-lives. So that's what that t represents. So it can represent any time cycle, depending on what kind of growth rate you're talking about. All right, that's exponential decay.